when we have a breeze when we have wind in essence in a breezy day. So part B, with free stream velocity of 8 meters per second. Now the problem doesn't specify which direction the wind is flowing, but we are assuming the streamline is a long streamline, so we are ignoring in essence what's going on in the longitudinal direction of the pipe. So I believe it's not specified, but we can actually consider this as a cylinder in cross flow where free stream is actually either going into the board or coming to us, right? So that's kind of the vector directions of free stream. But this is an assumption because the problem is not explicitly stating. So I'm going to go ahead and write cross flow. The other reason I'm picking up this is because we only know how to treat a problem, an external flow over a cylinder, if the cylinder is in cross flow, a long cylinder in cross flow. So that's essentially kind of a pragmatic pick, if you will. So under those conditions, we are going to go back our ME3 level knowledge, calculate the Reynolds number as infinity mu, and that's going to be 0.089 divided by 24.54 times 10 to the power minus 6, and that's 2.90 times 10 to the power 4. So you can go ahead and check that is whether that is actually laminar or turbulent flow. It's less than the critical Reynolds number for cylinder and cross flow. But what's important is that we can calculate, we know how to calculate the Nusselt number for that configuration. I'm picking one of the correlations that's based on Churchill and Bernstein. Okay. And this correlation can be used. It's kind of a lengthy correlation. I will actually paste here. And we are going to have, based on this result, we are going to have set number 97.67. And from here, the average convection coefficient is 0.67 times divided by 0.089, and that's going to be 35.7 per meter square. And from here, with the same reasoning, you can calculate convection coefficient as heat transfer rate per unit length is 300. I think the most interesting part of this question is part C. This result of part B. Okay. So in part C, we are adding an insulation layer. This is our steam line. That's the center line of the steam line. And that's the inner diameter now, because we are going to add an insulation layer on top. Yes, insulation. Fine. And therefore, that's the outer diameter that depends on the thickness of this insulation that is provided. Thickness of the insulation is 0.02 meters, and insulation thermal conductivity is 0.08 watt per meter Kelvin. Okay, so inner and outer diameter is the I is same as before, 0.089 meters, and the O is the I plus 2 times the thickness, that is 0.129 meters. All right, guys. I ask for your pardon. I will take 5 more minutes of break, and I will come back. I'm sorry for that, but I will have to do it. Okay. All right, thank you for your patience. Okay, so part C is about adding an insulation layer where now we can talk about the inner insulation temperature as, let's call this TSI, and that's equal to the steam temperature like before. But now we also have an outer insulation surface temperature because there's going to be conduction within the insulation, and then there's going to be convection and radiation from the outer surface of the insulation. We can represent this under steady state conditions. We can represent this as a thermal resistance network starting from inner insulation surface temperature, some thermal resistance for conduction within the insulation, to the outer insulation surface temperature. Now we are going to branch out, and that's going to go to T infinity. That's the convection resistance. And on the other side, we can even have a radiation resistance, right? We can represent the Stefan-Boltzmann law in a way that we can come up with a ratio of heat transfer rate and a temperature difference, and that's a result of that ratio is essentially the radiation thermal resistance. So the conduction heat transfer, let's call this Q1, is going to split into two, associated with convection and radiation here. And if you balance them out, there's going to be Q1 is equal to Q1 plus Q3. And if you were to write this equality, Q1 is equal to Q3, 2 plus Q3, as ratio of temperatures and thermal resistances, that's equal to TSO minus T infinity divided by the convection resistance plus TSO minus T infinity divided by radiation resistance. If we could directly evaluate the resistances, we could simply solve for the TSO, this nodal temperature over here, and then we would be able to calculate the total heat transfer rate, right? But the situation is not as simple because the radiative heat transfer is actually a nonlinear function of temperature. So let's write down the individual resistance terms to actually see that. That's remember that's a cylindrical slab. That's the natural logarithm of the ratio of radiuses or diameters, and that's divided by 2 pi k insulation and the length L. How is the convection resistance? Convection resistance is 1 over h, the outer surface area, but that's equal to 1 over h pi dOL. What else? The radiation resistance is going to be similar to the convection resistance. We are going to have a radiative heat transfer coefficient multiplied by pi dOL. However, this radiative heat transfer coefficient is a strong function of temperature, if you remember. That's simply Stefan-Boltzmann law divided by Ts minus T surroundings. So TSO plus T sur multiplied by TSO square plus okay, there you go. Plus T surrounding square. It's a strong, in essence, that's a strong function of TSO with the square term right over there. Okay, so when we substitute these expressions, we're actually going to recover the Stefan-Boltzmann law from this. I simply use this to illustrate the radiative thermal resistance concept here to remind you of that. But we are going to, at the end, recover the radiative heat flux, well, radiative heat transfer rate per unit length. So Tsi minus TSO divided by the natural logarithm of dO divided by di divided by 2 pi k insulation L is equal to h pi dl ts minus t infinity plus epsilon sigma, and I write d, that's d0, right? So d0 L TSO raised to the power 4 minus T surroundings raised to the power 4. Anyway, so L's get cancelled out. And we are ending up with an equation. We know TSI, we know the diameters, we know emissivity, we know all these parameters over here except for TSO. So for the various values of H that we obtain in part A and part B, this is actually a function of a nonlinear function of TSO. If we collect all terms in one side, we can actually set like a root finding problem. The TSO is going to be root of that equation. So I have done this. One approach would be that instead of that, you could take an iterative approach. This is yet another root finding approach, actually, where you would simply ignore the nonlinear term first, saying that no radiative heat transfer, calculate TSO from this equality, and then, by the way, that's TSO. And then you could substitute that in and recalculate TSO based on that. And you could iterate over that, but we have multiple H values that we would like to do this for. Remember, in part A, we found H as 7.7, something like 7.68 watt per meter Kelvin. In part B, we found H as 35.7 watt per meter Kelvin. So at the end, we are going to calculate TSO for that. What I did is actually I coded that. I was a bit lazy. I didn't want to do iterations. Instead, I actually wrote a MATLAB code to calculate that. So a lot of this code is boilerplate for setting up the problem and then plotting the results. However, this part is what is actually doing the action. So this code is what's doing is that I picked a range of H. So I wanted to see it not just for TSO, not only for two H values. I wanted to see the trends of TSO, how the surface temperature is changing as we change the convection heat transfer coefficient. So that's what I wanted to do. Therefore, I wrote down a series of H's, and for each H, I build a function TSO. That function is representing what we have written over here, this equation, and put all the terms on one side, and say that I would like to find the root of that function with that F0 built-in function in MATLAB. This is essentially root finding, what we are doing. And for each value of H, I obtain the corresponding value for the surface temperature. Then I plotted those, and here are the plots. Once we obtained, first of all, with the increasing convection heat transfer coefficient, we can see that the surface temperature is decreasing, because increasing H means increasing heat transfer across the insulation. And that increased heat transfer can only be sustained by a greater temperature drop from the steam temperature to the outside temperature. So TSO is decreasing because of that. And after that, we can go ahead and calculate the contributions of radiative and convective heat transfer to the total heat transfer. Q1 is the total heat transfer rate that we are after, and Q2 is the convective heat transfer, and Q3 is the radiative heat transfer. We also have the ability to plot the variation of these with respect to the convection heat transfer coefficient. The question was asking what would be the values of surface temperature. Well, it's not even asking that. It's actually asking, let me actually go back. It's asking what is the heat loss? Would the heat loss change significantly with an appreciable wind speed? So we are being asked to calculate heat loss for both conditions. I haven't done this, in pen and paper, but we can infer about that. So first of all, let's take a look at, in order to calculate heat loss, we need to identify the surface temperature for free convection at around H3 of 7.68 watt per meter square Kelvin, we are obtaining a value of, as far as I know, that was around 56. Yes, so for forced convection, we had an H value of approximately 35.7. Let me check. 35.7. Somewhere like that. And what we are obtaining over here is PSO is approximately 34 degrees Celsius. These are accurate up to 2 significant figures. I didn't go into details of obtaining them more precisely. And based on that, you can actually do the same reasoning for the curves right over here. And you can also run the simulation code. And you can see that we are actually looking at approximately 15 to 20% increase, something like that, from 190 to 220. So it's about 15% increase. In heat transfer rate or Q loss due to forced convection. Okay. All right. Any questions about this problem?
Hocam, what about the combined free and forced conditions?
We haven't covered that. I'm going to revisit this problem when we discuss that, John.
Okay, hocam.
All right. Okay, so let's last 10 minutes of the class. How about discussing about another configuration? So we are going to talk about parallel plate channels. So we have already covered a vertical plate. So the idea is, how about bringing two vertical plates together? So that's vertical plate 1, and that's vertical plate. That's vertical plate 2. And let's define the nomenclature. So that's length of individual plates, L, and they are separated with a certain distance, S. That's the spacing between those two plates. And what we can have is we can have various conditions. So that plate 1 has a surface, can have a surface temperature Ts1, and that plate 2 can have a surface temperature Ts2, or they can be associated with a prescribed heat flux of Qs1 and prescribed heat flux of Qs2. And these prescribed heat fluxes can be zero, for instance. One of them can be zero, meaning that one of the plates can be is adiabatic, insulated. The other discussion is, depending on the separation, the spacing, in particular this ratio of spacing to the length of the plates, we can have different flow structures happening. So let's consider this S over L ratio. If it is large, in a way that when the boundary layers are forming, they are going to look like this, right? So that's the large spacing, and the boundary layer is going to develop like this, and they're not going to merge. These plates are essentially almost like looking like isolated plates. So that's my color code for large, and that means they are like acting like isolated plates. They are not affecting each other. How about if the spacing is small? Now we can have actually something like this. The boundary layer are going to form and merge over here, and In particular, if the spacing gets as closer and smaller or smaller, or plates get closer and closer, we are going to have merge boundary layers. And remember what happens when there's merge boundary layer. There's just like the force convection internal flow, where we would have fully developed conditions, we would have a similar situation. We would have fully developed flow within this structure. So merged boundary layer and fully developed flow. So by the way, I wanted to indicate that I'm actually measuring X from this. That's going to be useful in later discussion. We can have various configurations. These parallel channels can be vertically oriented such that with respect to G, they are like that. However, they can also be inclined. So let's note that down. I just mentioned, though, I would like to repeat that we can have symmetric or unsymmetric prescribed boundary conditions, right? So, for instance, we can have constant surface temperature, but one of the surfaces are insulated so that there is no heat flux, right? So this can be heated. Heated means we are either having an Ts greater than T infinity, right? So under those conditions, that's how there is going to be flow within. Or we are simply prescribing some heat flux that is non-zero heat flux. If there is zero heat flux, it doesn't mean there cannot be any surface temperature difference from the ambient, right? So that's kind of a null condition or like trivial condition. You might be wondering what kind of typical scenarios we encounter. Why are we so invested in analyzing these parallel plate channels? And I'm going to show you this. Here is a heat sink. And when we did fin analysis in chapter 3, we didn't really care about obtaining the convection heat transfer coefficient associated with the fin surface, right? But now we will be able to do this. And it will depend on the spacing between those two parallel plates. And this is how we are going to be able to discuss that. So let me check. How about we stop here? And I will answer any questions that you may have about today's lecture, or if you have other questions from previous lectures, I'm happy to stay here and answer those questions for you. Do you have any questions? By the way, I would like to make sure that this is color-coded, so the small indicates this trend in the flow.
After my friends asked, can I ask not about lecture, but something else?
Yes, go ahead.
Like someone is typing.
Yeah, you can go ahead and ask your question, and I will answer the question when it comes up.
Hocam hocam can I attend to ya hocam laboratuvar şeyini raporunu tek başıma yazma ihtimalim var mı?
I'm not so sure about that. You have the flexibility to do the homeworks on your own. You haven't posted on homeworks yet, but you have the flexibility to do that. For laboratory reports, let me check with our assistants and let you know in the next class.
Teşekkürler hocam.
Okay. Burhan is asking, in parallel place, is there any inter-region correlations we can use? So indeed, we are not going to have like distinction between fully developed flow versus inter-region. I'm going to have a whole bunch of correlations in the next class to show you They are not going to distinguish fully developed versus entry region. They are going to be based on this S all over L ratio. S all over R ratio that is implicitly encoding that information, right? So where the significance of entry region to the fully developed region in those plates. So this is the main parameter that we are going to be focusing in our correlations. Yeah, so let me show you one quick example. Sneak peek for the next class. I will leave it here and we are going to start from here. This one is for vertical symmetrically heated isothermal plates. Plates, that is Ts1 is equal to Ts2, and these are greater than T infinity. We will discuss more. I will repeat this in the next class, but to answer the question from Burhan, yes, so this is what the typical correlation looks like for parallel plate channels.